Alright, so we got about 10 seconds before the class starts. I have started the stream on Discord side and also on YouTube side. Alright, and it is noontime. I'm gonna get the class started. So the first thing I want to bring up is something that I sent announcements to already. I sent announcements about this already. I noticed this morning when I checked the prerequisite checks, um, some people still have not had CISP430 co-requisite um, checked off. So if you see a 1 in the assignment, as a score, that means it has been checked off already, so you are in the clear. On the other hand, if you look at your grade sheet and the CISP co-requisite, CISP 430 co-requisite has a 0 in it, or if it is blank, then you have not have this co-requisite cleared. So you need to file a challenge form to make sure that it is the requirement is met before the 11th of this month. So that's only a few more days. So you got to do this as soon as possible because otherwise I will drop people who have not met this requirement. My voice is echoing. I do not know why. I'm streaming to YouTube and also to Discord at the same time. So if you're listening from both at the same time, then there might be a lag between the two sources and you might hear something that sounds like an echo. Alright, so I'm getting a few other people typing. Maybe they're talking about the echoing, maybe not. So they're still typing. Alright. If you have a 1 on the prerequisite assignment, that means you have met the requirement, yes. But there are two requirements. One is for the math prerequisite and one is for the CISP 430 co-requisite. And then Aiden says, I sound okay. So the issue of echoing can be a local issue, I'm not sure. Alright. Alright, so what we'll do today is to finish the last section in the discussion of functions. This is the last section. And what section 3.2 is trying to say is why do we need to understand functions in this particular class? In other words, we talk about functions in a lot of the math classes. So the math classes, we use linear functions, we use parabolas, we use all kinds of polynomials and whatnot. And there's a certain purpose, right? In those math classes that we deal with, functions. So the question is, why do we need to use functions in this particular class? So as it turns out, the use of the concept of function in this class is a little bit different from how we use functions in your other classes. The way you use other functions in other classes is really kind of in a more mathematical way, where there's a set formula to compute the value of a function based on the value they're supplying to the function. In other words, you give the function a value in the domain and it returns a value in the codomain based on an expression. But in this class, the functions are much more arbitrary. Okay, and that's basically what the second paragraph is saying. In this class, functions are much more arbitrary in the sense that the function may not model the relationship between real life quantities, which your math classes do. So in your math class, you study functions where if you throw a rock, the trajectory of the rock can be modeled by the parabola. But in this class, it is a little bit different. So what we want to do, what I want to do, is to illustrate, how functions are utilized in this class. So you guys have all studied, sorting. Assuming that you have taken CISP 430 or you're taking CISP 430, then you would have encountered, sorting probably by this point. And the idea is, how do you know, that a sorting function is getting the job done? We have many different sorting algorithms, right? So we have bubble sort, we have merge sort, we have quick sort, we have selection sort. There are a lot of different sorting algorithms. I don't really care how it is done. I want to know, what can you, how can you qualify that a sorting algorithm is getting the job done correctly? That is the question. So what we want to do is to specify the condition, so that we can say, yep, we know this particular algorithm is getting sorting done correctly. So the first thing we do is we want to be able to remember the values of each element prior to the execution of a sorting algorithm. So what we are trying to do here is to say, okay, these were the original values in the elements of an array before we run the sorting algorithm. And so that's how we are using the k of I constants. So we basically say initially, before we run the sorting algorithm, the value of array element at position I from array A is k of I. So k of I is really just a notation so that we can remember, how what the value of each element is before we run the algorithm. So we then run an algorithm that can do an in-place sort. So that means, the array elements are getting changed by running the sorting algorithm. So one thing we can do, to qualify that we are working with, that the sorting algorithm seems to be working correctly, is this particular expression here. When this quantified expression is true, some people may say, okay, the array is now sorted. So let's take a closer look at this expression here and see how it is expressing, that an array is sorted. So the quantifier on the outside says, for all I in the set, and this particular set, starts with 0 and it ends with bar a bar minus 2. So I use the bar a bar notation as the length of an array. Basically, it is the same as the number of elements in an array, and the reason why it is subtracted by 2 is because we are looking at the index of the second last item of the array. So that's why it is from 0, which is the index of the first element in the array, to bar a bar minus 2, which is the index of the second to the last item in the entire array. So do we have any questions about this part, why we have the quantifier set up like this? Okay, I don't see any questions. Alright, so the actual condition that we want is a bracket I, the element at index I, is less than or equal to the element of that is right next to it, which is a bracket I plus 1. So this seems to make sense, right? Because we are relating the elements in an array based on how they relate to the one right next to it. And assuming we want the array to be sorted in a non-decreasing order, this would appear to specify the correct outcome of a sorting algorithm. So there are two things at play here. One is if an array meets this requirement, is the array sorted? The answer is yes. But then the second question is the sorting algorithm working correctly? Well, that turns out not to be the case, because this particular expression mentions nothing about k of I, right? K of I is all the way here, and we don't see k of I down here. So that means, we do not actually need to use any, not even one, of the values of the original array. We can initialize the entire array to 0, and it would meet this requirement. But that's not how you sort an array, because when you sort an array, the resulting array should have quote-unquote all the same values as the original array. So now we need to specify another condition. So we can now add this particular criterion here. So this criterion is kind of interesting. Okay, so let's take a closer look at this particular expression here. This time the quantifier I is from the in a set of 0 all the way to bar a bar minus 1. In other words, it is basically the index of every single element in the array, and not just the first it's not just the index of the elements except for the last one. This one does include the last element in the array. And then the second condition here is a little bit more complex this time. So this time we want a bracket I to equal to k of f of I. So f of I is the function f applied to I. So it is mapping the index I, which we start with here, to a particular index so that we can refer to a particular k. So this is an attempt to basically say, after the sorting algorithm is done, each element of the array should have the value of some original value of elements in the array. And that mapping is done by f of I. But the problem is f can map everything to the same item in the codomain. So that means f of I can just be defined as 0. So if f of I is defined to be 0, then it's really easy to have a condition that will meet this requirement, because all we need to do is to take the first element of the entire array, and then we just copy that value throughout the entire array, and then we are done. But that's not sorting, right? That's just copying the value of the first element throughout the entire array, and that's not sorting. So now we understand that, okay, we are lacking a particularly vocabulary in order to express that there has to be a one-to-one correspondence. Okay, I'm using that word one-to-one in a very loose way in this case. So, but that's kind of what we want to express. Okay, is between this I and between this f of I, there has to be a one-to-one correspondence. So let me just kind of pause here and see if there are any questions about what I have talked about up to this point. So if you have any questions, go ahead and try to ask those questions now. I'm taking a look at the text channel. Okay, so we got one question coming potentially. And I am also checking my mixer to make sure that my voice feedback is turned on, and it seems to be turned on. It just sounds kind of soft to me. All right. Alright, so Tom is asking, is this converted to pseudocode or code for more clarification? This has nothing to do with code per se at this point. This really only has to do with, how should I put this? This has to do with how do we qualify the output of a sorting algorithm as correct or not. In other words, how can we use mathematical expressions to say, okay, if the output of a sorting algorithm makes this true, that means the sorting algorithm is getting the job done. So we are not even interested in the algorithm itself. We're only interested in describing or being able to qualify whether the output of a sorting algorithm is correct or not. Yeah, so it's kind of like a validation check, yes. But it is a validation check in the form of math algorithm. It is about specifying the mathematical expression, which is Boolean. It's either true or false, so that if the expression is true, if and only if the result of a sorting algorithm is correct. Okay, so that's very good. Now this is really kind of important. Okay, even though I made this kind of the last subsection of section 3, it is actually very important, because this is one of the reasons why AI in a certain field of AI is resurrected. So let me show you a few things, just so that we have a context of talking about this. So the first thing I want to show is hard bleed. Okay. So the hard bleed bug is something that happened, I think, a few years back, but it was a vulnerability in the OpenSSH library, where a bug allowed people to kind of poke a server and potentially be able to retrieve encryption keys from an SSL server, which is kind of bad, okay? Because if you can retrieve an encryption key, the private key in encryption, out of a SSH, server, then you can basically assume the identity of a website and pretend to be, a bank or a financial institution, website and stuff like that. So that potentially is bad. And Jonathan mentioned a Tom Scott video. Yeah, so you can go ahead and check out, Heartbleed and then Tom Scott and see what you find. But it's basically a software bug that caused this potential issue to happen. So what does this have anything to do with what we are doing, right? What is the connection? So the connection is we want to be able to use mathematical language to specify the correct outcome of not only the sorting algorithm, but of any important algorithm. So in this case, it would be the OpenSSH library logic, and we want to be able to define what is the correct behavior regardless of the input. And if we can do that, okay, assuming we can mathematically describe the proper outcome, of an algorithm, then we can try to mathematically prove that an algorithm has the correct outcome or not. Okay, so let me switch to the tablet and see if that can be helpful here. So what we'll do, so I'm going back to just making the tablet window just another window on top. So this way, I will be looking at exactly the same thing that you'll be looking at. So that won't, I won't forget to turn off the tablet or turn off the tablet screen, when we are in this mode. Okay. So what we do here is we have an algorithm. Okay. So we have algorithm, and we'll call this algorithm A. Okay. So we have precondition. In other words, the precondition before we run an algorithm is really just a huge, gigantic expression that's Boolean. Okay, that is true for every single possible input to an algorithm. Okay, in other words, we're just specifying. Okay, what can the algorithm assume to be true before it starts running? Okay, so all of that stuff, basically combined to one single gigantic expression that is called the precondition. And now we have algorithm A. Okay, so algorithm A, can be specified in pseudocode. It can be specified in any form. It doesn't really matter, how it is specified, but we can kind of count on, algorithm A to have loops. It can have conditional statements. It can have assignment statements. You can have, all kinds of common stuff that we use when we specify algorithms. So the precondition goes into the algorithm, and then magically, okay, so we'll put a few stars here. So magically, let's just say that we can mathematically derive the post condition after an algorithm is analyzed. So there's no actual running of the algorithm here. We are not trying to come up with test cases, feeding into the algorithm and then look at the output, of the test cases. We are actually, using mathematics to step by step derive a post condition. So this is not your typical work of writing an algorithm or tracing an algorithm or debugging an algorithm. This is actually mathematical proof. Okay, going from the precondition step by step, looking at the algorithm to get to the post condition. So this is a process of mathematical proof. So now on the side here, we'll have a validation. Okay, I can't spell. Okay, so we'll have a validation condition, which is separately derived. Okay, so the validation condition is what we are talking about in the module that we were talking about. Section 3.1 is essentially trying to come up with the validation condition of the sorting algorithm. So now the biggest question, okay, so I put the question marks here because this is what we want to know, is whether the post condition derived based on an algorithm and its precondition is equivalent to the validation condition. We don't want imply, okay? We want it to go both ways, okay? Because if we can establish this particular equivalency, then we have proven once and for all that algorithm A is correct. Doesn't matter what test case we throw at it, which is kind of what we want to do now. Okay, because there are a lot of algorithms, or subroutines and modules of code that really need to be really solid. Okay, at the OpenSSH library being one of those, and other components in an operating system would be also part of that as well. So now I want to open up another page here to look up the term to refer to this sort of thing. So we can say algorithm, verification, validation. So these are all words that you might find when we refer to what we're talking about. So in Wikipedia, we have verification and validation. These are independent procedures that are used together to check out the product, service, the system meet requirement and specifications, and so on. But in the sense of software, let me see if I can find something. Software verification and validation. So this one is more specifically applied to software. And you can kind of imagine that this field of study is particularly important now because the internet is everywhere. Okay, we are hooking up things, so that if a particular component in a computer is not working correctly and it shows a vulnerability, if that thing is installed on a lot of machines, then a lot of machines can potentially be hacked at the same time using the same method, and that is always not a good thing. So this is kind of something that we are, we as in computer scientists are trying to accomplish. It was attempted in the late 80s and the early 90s using, there are two main branches of AI. So when most people think about AI today, they are referring to neural nets, okay, which is about pattern recognition and stuff like that. Now, I'm not downplaying the importance or the capability of neural nets, but that's only one aspect of AI. The other aspect of AI is, how do we prove theorems? Okay, just think about your math classes. Okay, your math classes typically will have exam questions or homework assignments that involve some kind of proof. So we want to use computers to prove theorems, and in this case, we want to basically use theorem proving to go from the precondition using the algorithm to arrive to the post condition, and then the human. Okay, we'll put a human here. So the human will come up with the validation condition, and then the machine, okay, so the computer would be doing this step, and the computer would also be doing this step here. Okay, so the computer would basically try to prove that the post condition of running the algorithm is equivalent to the validation condition. And that's kind of what we want to do. There are certain limited success, if the algorithm is simple enough, but we do not have the capability of applying this technique to an entire operating system, such as Linux. Okay, we want to prove that Linux is correct. Okay, all aspects of Linux is correct. It can never be hacked. Okay, that would be nice to know. But Linux is a really large piece of software, and as a result, we don't yet have the capability to apply the technique that is being shown on the tablet to the entire operating system. But at least, we would like to apply this to key pieces of an operating system, like the TCP/IP stack, anything that has to do with encryption, anything that has to do with secured communication or secured file storage. We want at least those portions of an operating system to be able to be checked by this particular method. So that's kind of the context of section 3.2. I misspoke. I said 3.1 earlier, but this is actually 3.2. So this is kind of why we want to have at least the vocabulary to do this, and the and this goes all the way back to the first question that I asked in today's class. Why do we study functions? So the way we study functions in this class has to do with trying to use it as part of the vocabulary to express whether an algorithm is correct or not. At least that's one of the many ways to utilize what we're learning in this class. So that is the end of module 0289, which is functions as sets. So now what we're going to do is to move on to module 0290, which talks about sub-classifications of functions. There are functions that are injective, there are functions that are surjective, there are functions that are bijective, and then there are functions that are not. Okay, they're neither injective nor surjective. So technically speaking, there are 4 different types of functions, but they are all functions. Okay, if you have a set of 2 tuples, but it is not a function, we don't even bother to talk about whether they are injective, surjective, or bijective. Nojective, non-jective. That's kind of cool, Aiden, coming up with that term. Alright, so what we'll do is we're going to start with injection. So as you probably expect, these terms, or the understanding of these terms, really kind of require that people understand what a function is to begin with. And so having reviewed the material from last Wednesday is super important to get started with this chapter here, or this module over here. So what we'll do is we'll say, if we know that f is a function already, okay, this condition here, which looks kind of complicated and kind of ugly, or you can look at it like this one here, they are equivalent. So these two, if they are true for a particular function f, then we can say the function is injective. So we already start with this notation here, which you probably recall from last week's discussion, that this means f is a map, x is the domain of the map, and y is the codomain of the map, and f is a function, which basically says, every element of x is mapped to one element, one and only one element in y. Okay, so we already know that about f. We assume that. And then this condition is an additional condition to basically say whether function f is injective or not. So we'll take a look at the first one first. What I'll do is I am going to copy that to the tablet, so this way I can kind of mark up the expression. So there's no quick and easy way for me to copy and paste from my desktop, so I'm just gonna have to write it. I mean, the only way to do this, using a tool, is to download the PDF or upload the PDF to the tablet, and then what we do is we can then copy and paste content of the PDF to portions of what I'm handwriting. Okay, but it's not too bad. I mean, it's a relatively short expression. So we look at this expression and then we go like, okay, this is really long, this is complex, it's using a whole lot of symbols that I'm not familiar with. What are we going to do about this? Well, first thing first, you got to make sure that you understand all the symbols, right? So we'll go ahead and check out the symbols. We have a quantifier symbol here and a quantifier symbol over here. So by together, okay, all they are saying, okay, this portion here, all they are saying is we pick a p from the set, from the elements of x, we pick a q from the element of x. So these p, the way we choose an element for p and the way we choose an element for q are independent. So they can end up to be the same one, they can be different. We're looking at all the possible combinations, okay? And then we want this, okay? We want this part to be true regardless of how we choose elements P and Q from X. Okay, so that's what we want to be true. You can see the last operation is an implication. So that means, if you want an implication to be always true in this case, then the easy ones would be the cases where the left-hand side or the precedent of the implication is false to begin with. So that would be P does not equal to Q. In other words, if P does equal to Q, we don't even bother to to evaluate the right-hand side of the implication. All right. So the only time we evaluate, f of P does not equal to f of Q, is when P does not equal to Q. So we got some people typing in the text channel. I'm gonna pause here and wait for the question. All right, should there be parentheses around f of P does not equal to f of Q? I suppose, an extra pair would not hurt. Let me check the original text. The original text does not have an extra parentheses, but we can certainly do that. I mean, we can put it here, just so that it is more clear. All right, so now the real question is when P does not equal to Q, because when the precedent is true in an implication, then the implication can be false if the consequent or the right-hand side is false. So we want to make sure that when P does not equal to Q, f of P does not equal to f of Q. That really is the essence of injection. Okay, being injective means two different elements from the domain have to map to unique elements in the codomain. That is basically the bottom line. So do we have any questions about this kind of colloquial interpretation of injection? Elements in the domain must map to unique elements in the codomain. There's a uniqueness in injection. So I'm looking at the text channel and I am not seeing. Oh, okay, there we go. We got one question. I'm not sure whether it's one-to-one. I haven't looked up those terms, but it is technically called an injection. Because I know there's onto, there's to, so you can look up whether those terms are equivalent or not, whether one-to-one is considered the same as injection. I'm not sure. But in this class, I would only refer to these functions as injection. Okay. All right. Okay, thank you. Thank you, Xavier. All right, so that takes care of kind of injection. But let's look at this one here, okay? Because this one looks kind of like one of the expressions that we have seen already to when we talked about what a function is. So we'll take a quick look at this one. It really means the same thing as this one over here, but we'll kind of check this out. So the first thing we know is the quantifier is applied to the codomain. In other words, unlike the qualification of whether something is a function or not, which uses a quantifier on the domain, to this one focuses on the codomain. So it's basically saying, for each element in the codomain, we want to create a set, okay? And the set basically is saying that, okay, for whatever Q we have chosen already, let's find all the two tuples where Q is the second item in F. Okay, so we are going through the entire function F as a set, and then we are going through all the two tuples, and then we just put all the two tuples where the second item in the two tuple is the same as Q, and we put all of those into a set. So then we apply the cardinality operator. We basically want to count how many things are in that set, and the cardinality needs to be less than or equal to 1. Okay, in other words, it is okay to be 0. It's okay for this cardinality to be 0, which basically says, hey, this thing in the codomain, nobody maps to it. It's perfectly okay. Okay, it doesn't disqualify from being an injection just because something in the codomain is not mapped to. It can be one, but it cannot be more than one. So the moment you have two things in the domain mapping to the same thing in the codomain, that function is not injective anymore. So that's why this expression is really saying the same thing as this expression here. Depending on the individual, okay, some people like this a little better, some people like this a little better, but the bottom line is the same. So now we have an example here. So the example says, we know that f is a function already. We know the domain is AB. We know the codomain is 1, 2, 3. So these three examples will illustrate which one is and which one is not injective. The first one basically says f is not even a function, because if f has a2, a1 in it, then it is not mapping every element in the domain to one and only one thing in the codomain. So it fails the test of being even a function. So the first item basically says, since f is not even a function, we are not even going to talk about whether it's injective or not. The second one is a function. You can see A is mapped to one thing in the codomain, B is mapped to one thing in the codomain. But since they're mapped to the same thing in the codomain, there's no uniqueness, and as a result, this particular function f is not injective. And then the last example here is injective. So A is mapped to 1, B is mapped to 2. So each element in the domain is mapped to a unique element in the codomain, and as a result, in the third case, the function is injective. And it's perfectly okay that 3 in the codomain is not used, because we can afford that cardinality to be 0. All right. So are there any questions about section 2 about injection? I'm not seeing any questions. All right. So if there are no questions, we move on. So then section 3 talks about surjection. So surjection can also be expressed in two ways. Let's look at the first way first. So the first way is saying for everything in Y. Okay, so this time the ordering of the quantifier is a little bit off. So it is saying, for everything in Y, for every Q in Y, which is the codomain, there exists at least one P in X, so that f of P, remember P is from the domain, equals to Q. In other words, it is basically saying everything in Y needs to be mapped to. You cannot have something, in the codomain that is quote unquote, left over, where nothing in the codomain maps to it. So that's kind of the, I guess this is more intuitive to some people. And then the less intuitive way is to use the cardinality method. So you can see this one. Okay, let me just point out which two we are talking about. So if you look at this expression here and you look at this expression here, they are almost the same. The only difference is this one wants the cardinality to be less than or equal to 1, and this one wants the cardinality to be greater than or equal to 1. And that's it. Okay, so this cardinality being greater than or equal to 1 is basically saying, I need each element in the codomain to be mapped to. We can map so the requirement is at least one. At least one element in the domain needs to map to the an element in the codomain. So it can be 1, can be 2, but it cannot be 0. So that's the only difference between these two conditions. So do we have any questions? I'm not seeing any questions in the text channel. Alright, so if there are no questions in the text channel, we move on to bijection. Oh, wait, hold on a second. We also want to go through some examples. So we want to look at these two examples. In both examples, there are functions. The domain is AB and the codomain is 1, 2. In the first case, we have A1, B2. This is surjective because everything in the codomain is mapped to. In the second case where we have A1, B1, we're mapping both A and B to the same element 1 in the codomain, which leaves 2 as an element in the codomain unused, unmapped to, and as a result, in the second example, F is not surjective. So do we have any questions about the concept of surjection? All right. If there are no questions, we're going to move on to bijection, which is a real easy one. Because in the case of bijection, it just means it is both both an injection and a surjection. That's all bijection means. So when you look at the qualification, okay, the condition, the expressions, it is basically just recycling the ones that we have seen already. We want this and this. But because one specifies, a particular quantity to be less than or equal to 1, and the other one specifies the quantity to be greater than or equal to 1, that means the quantity has to be exactly 1. That is the bottom line of bijection. So in bijection, every element in the domain has to map to one and only one unique element in the codomain, and we cannot have left over in the codomain where nothing from the domain maps to the codomain. So do we have any questions about these three terms? So the three terms that we have introduced at this point is injection, which is about uniqueness, surjection, which is about using up everything in the codomain, and bijection, which is basically both injection and surjection at the same time. Alright, I'm not seeing any questions in the text channel. Let me just kind of hover over the text channel, make sure that I am not missing anything. Nope. Okay. Alright. So now we can move on to inverse. Okay, the concept of inverse. Oh, wait, we got a question. Very good. We got 2 people typing. Alright. Yes, yeah, we appreciate Danielle to be here because she is our closed captionist, real-time closed captionist. All right. Can I go over how it is reversible? Oh, okay, I see. So reversible means, if you flip the mapping, it becomes another function, guaranteed. Surjection, but not injection. Sure, that's easy. So let's take a look. So we'll do both at the same, not at the same time, but we'll answer both of those questions. So we'll both answer the question of what is a surjection that is not an injection. That's actually pretty easy. So let's say we have a function and we want to make the domain ABC, and we want to make the codomain just 1, 2. And then the mapping itself is a set where we have A1, A maps to 1, B maps to 1, C maps to 2. This is surjective. Oh, you guys cannot see it. No, I keep forgetting that. There we go. All right. So in this case, we have f being a function. ABC is the set that we call the domain, and then 1, 2 is the set that we call the codomain. If f is defined as a set where we have elements A1, B1, and C2, then this particular f is surjective because we can see 1, 2 in the codomain, they're both mapped to, but this is not an injection because because AB both from the domain map to the same thing in the codomain, which is 1. So that answers the question of, okay, and then Damon is, yes, so P is not bound by quantifiers. It's basically, anything that can match P is fine. So that's what an unbound variable does in this kind of expression. It's basically just saying, okay, find me whatever PQ that is in F, and we'll stick it in this particular set. So P can bind to A, and P would also bind to B, and that's why we have two elements in the set that we're constructing. Not exactly for all, Aiden. It is not a for all. It's basically just saying, match all. It's kind of more like a wild card to say, whatever we need P to be, so the PQ is in F, that we will put that, will bind to that particular P. No, Q is bound from the outside, so Q is bound by the quantifier. So when P is I want you guys to focus on the text channel, because this discussion is using the screenshots that people have put into the text channel. So for all Q in Y is already binding Q to a specific Y before we apply the condition of the quantified statement. So is that okay, Tom? You can kind of look at for all Q in Y as a loop, and then the body of the loop is trying to figure out the cardinality and see if it is less than or equal to 1. So by the time we get to the body of the loop, Q is already a specific item in Y. Okay? Alright, so that answers one particular question, and then we are going to go back to Yolanda's question. Can I go over how something that is bijective is automatically reversible? So we'll use the tablet again. Okay, so now let's go back and focus on the tablet, which is what is being shared with you on screen. So let's just say that F is bijective. Okay, then we can define, okay, F inversed. Okay, which is so the symbol of F, superscript -1, that's a typical way of expressing an inverse of a function, and that's used in basically all math classes. So I'm just going to use the same notation here. Okay, so we'll say this is how we define F inversed. So given F is a bijective function, okay, this is how we're going to define F inversed. So the way we define it is for all, I'll say PQ again. Okay, so for all 2 tuple PQ in F, I'm just trying to think of the best way to look at this. Okay, I think I can do it a little better. So let me erase this first and then redo this. So we'll say for all P, for all Q. So at this point, we don't even bind P or Q to anything. So P can be from outside of the domain, and Q can be outside of the codomain at this point. But this is where things get a little bit interesting. So we say PQ is in F, and we use extra parentheses in this case, if and only if QP, which is reversing the 2 elements in the 2 tuple, is in F inversed. Alright, so this is how we can define F inversed. So basically, we are saying if PQ is an element of F, then QP is an element of F inversed. If PQ is not in F, then QP is not in F inversed. If some QP is in F inversed, then PQ has to be in F, and if QP is not in F inversed, then PQ cannot be in F. So that's one way to look at it. So let's look at a concrete example. Okay. So we'll define f as a function where it is mapping from a, b as our domain to the codomain of 1, 2. And the actual mapping itself is a1 and b2. Okay. So the inverse of this particular f is really taking everything in f and just flip the order. So it becomes 1a and 2b. And this concept is probably best if you look at it from a more graphical perspective. So if you look at the way we define f, this is AB, which is our domain, and this is 1, 2, which is our codomain. So the way f works is A maps to 1, B maps to 2. That's f. Okay, so we'll indicate this is f, and this is f. So if we flip and say, well, what if we look at 1, 2 as our domain and AB as our codomain? How do we construct the inverse? Well, we just flip the arrow. This is f inversed, and this is also f inversed. I'm going to erase the other f, which is confusing. So is that okay? Does that kind of explain why it is quote-unquote reversible? In other words, if f is bijective, then f inverse is not only guaranteed to be, not only do we guarantee there's an f inverse as a function, we also guarantee f inverse is also bijective as well. So both function f and its inverse are bijective in this case. All right. So if there are no questions, we're gonna move on. So section 5 talks about the concept of inversing. It's kind of the same thing as what we talked about, except this portion here and this portion here are using the more mathematical way of looking at a function and its inverse. And then this one is what qualifies something to be a function, and this one here is what qualifies something to be bijection. But if you look at this in a certain way, it is also telling you that f inversed is also an inverse function, because instead of PQ we have QPs, which is down below a little bit. So if you look at this expression and this expression, let me see which one we're talking about. Oh, okay, down a little bit. So when you look at this one and look at this one here, essentially all we changed is instead of PQ we have QP, instead of F we have F inversed. So basically this is everything that I just talked about, except in a much more mathematical way. So do we have any questions at this point? Now that we have gone through injection, surjection, bijection, and then the inverse of a function, do we have any questions about those concepts? I'm just staring at the text channel and see if there are any questions. And there appears to be no questions. All right. So if there are no questions, we'll move on and go back to the example of sorting. Okay. Let me see. Can I still go back to that slide? Yep. There we go. So this is at the end of this, we have something that looks like this. So we're almost there. Okay, we're almost there. And the only thing that was lacking when we talked about this the first time was the term bijective. So we just want this f to be bijective. If we can guarantee this f is bijective, and on top of that we have this condition, then we can qualify, we can validate the output of a sorting algorithm is correct. Because this makes sure that everything is in order. This, on the other hand, with a bijective f, is making sure that every single value as an initial value of the array is represented when the array is sorted. So that together defines the correct outcome of any sorting algorithm. So that's kind of go back, right? The end of this module that talks about injection, surjection, and bijection kind of loops back to the last point of the previous module, which didn't quite get the job done because we did not have the vocabulary of bijection. But now that we have the term bijection, we just have to say, oh, okay, we just have to add that f needs to be a bijective function, and we're done. So I wanted to see if you guys have any questions before we go any further, because it seems like we are moving along just fine, at a pretty good pace. Let me take a look at the time. We got 25 minutes left. No questions. Alright, so if there are no questions, I am going to move on to the next module. And at the same time, I can give you the function assignment, so we are ready for that at this point. I'll give you guys I want to give you enough time to do it, but at the same time, I don't want people to procrastinate. That's kind of the difficulty of setting a due date, because you know everything that is needed to do the assignment already. So a due date of Wednesday is reasonable. It's actually doable. But I also want people to be able to reread those two modules and kind of absorb the material as they kind of go through the questions. So I'm gonna give you guys a week to do it. So we'll make it due 1 week from today, which is the 15th. So we'll make it due at noontime next week. So it is due right before class. There we go. And then we save and publish. And now we have the homework assignments published. Oh, you know what? Let me unpublish first. Because there are because some notations seem to be wrong. So I'm just kind of quickly going through the notations here and make sure that okay, it's probably not this module that has a problem. Okay, so I can publish now. Okay, that's fine. Alrighty, so it is published now. Alright, so if there are no questions, we are gonna move forward, because some people may be asking, so now that we know functions, we know what the bijection is and so on, what are we gonna do? Oh, by the way, let's also do the row taking thing. So we'll do the row taking thing right now. Zero to 08, and this is gonna go into row taking. Oh, fail to create new item. Huh. Now it's okay. Weird. Alright, so let's go ahead and make this one due at the end of today's lecture. I'll give you guys the time to do it. So today is the 8th. And the class ends at 1:20 p.m. Like so. And I need to come up with a word to ask. So new question. We'll make it fill in the blank as usual. What is tax word for row taking? And I'll give you guys several options. Okay, they're all considered correct. So we got injection, surjection, and you probably can guess what the next one is. Bijection. Bijection. There we go. So all lowercase, injection, surjection, bijection are correct answers. And I need to remember to update question, because if I don't, then we end up with no question at all. And then we click save and publish. No, there's no nojection or nulljection. Alright, I will even put it in the text channel for those of you who just missed what I did. So it's injection, bijection, surjection. Choose one. There we go. Rejection. I suppose rejection can be a function where the domain and the codomain are the same, so it's mapping back to itself. Alright, so let me know when you're done with the row taking activity, and then we'll go forward. Yes, I think I did. Oh, I didn't. I forgot to save and publish. There we go. Thank you. Objection. Alright, so I'm going to type this. Alright. And this gives me a little bit of time to kind of get to the next module. So we are really just sequentially going through the topics. The next module has a funny name of Aleph Null. Thank you. Very good. And I'll wait for a few more people to confirm, because I know some of you are very, very fast with Canvas stuff, and some other people may not be as fast. So I'm okay with just having a few more people to confirm. Okay, thank you, thank you. So now we're going to go ahead and talk about Aleph Null, which is a very funny name. And just so that people have some extra time, I'm going to republish this particular module so that people can right-click on a math equation and find out how it's typed. Because I think some of you are curious about how to enter the Aleph symbol. I mean, it makes sense. Okay, it's just backslash and then Aleph, A-L-E-P-H. There we go. So I'm just republishing the HTML document. It has exactly the same content, except this time we can right-click on things and find out how it is rendered in LaTeX. So right-click, show math as text command, and you can see Aleph Null is just backslash Aleph, A-L-E-P-H, and then an underscore and then the 0. Okay, so that's Aleph Null. All right. Cool. So now we're going to focus on, well, we now understand what a set is. We now understand the operators related to set operations. We understand functions, right? We have injection, surjection, and bijection, which also are the words for today's row taking activity. So what are we going to use those things for? Okay, so what this particular module, which is a little bit long, because I expanded on a particular topic where most people do not really care. But the idea is, what do we do to compare two sets? Each one has an infinite number of elements. How do we compare the cardinality of those two? So technically speaking, you cannot compare infinity with infinity. There's no equality between infinity and infinity, because infinity is, oh, okay, thank you, Jacob. Because infinity is not a value, okay? It is a concept, but it's not exactly a value. So you cannot compare infinity to infinity. Alright, so to make this, I'm gonna switch back to the tablet first. Oops. Nope, 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 nope. There we go. Alright. So on the tablet, we're going to take a look at the set of all integers. Okay, so the set of all integers is usually indicated by a funny looking z, symbol. So we want to look at the cardinality of this. Then you go like, well, but there is an infinite number of integers. Okay, because if you claim that x is the largest integer there is, then what about x plus 1, right? So there's no end to it from both directions. Okay, because you have because we can have positive integers and then we have negative integers. So the number of integers is infinite. All right. What is WR? Oops. All right. Oh, world record. Thank you. Alright, so we have the set of all integers, and now we have the set of all natural numbers. So the set of all natural numbers from 0 to 1 to 2, that's kind of how, when I learned about the set of all natural numbers, it includes 0, and then the set of all counting numbers, excludes 0. It starts with 1. It doesn't really matter, okay? So now we want to, look at the relationship between these two cardinalities. Okay, is one less than the other one? Is one greater than the other one? Or are they the same? That is the question. So most people would think, okay, so don't write this down as the answer, okay? Most people would think, I think there are more integers than there are natural numbers. And people would explain that and basically say, for every a as a natural number, this a, which is a natural number, is also an element of z, of integers. In other words, every natural number is an integer. But the other way around is not true. Okay, so the other way around is to say it is not the case that every integer is a natural number. Okay, so based on these two things, okay, every natural number is an integer, but not every integer is a natural number. Most people would think the cardinality of the set of all integers is going to be greater than the cardinality of the set of all natural numbers, right? So I'll let you guys kind of think about this a little bit. Okay, so I got an email from another class. Let me just kind of quickly respond to that. All right. Okay, so let's get back to this question now. But now I'm going to give you guys a way to do a mapping. Okay, and the way we do this is we'll just go ahead and write a function to do this. So we'll write a function f. Okay, and we'll go in one direction first. So we'll go from integers to natural numbers. Okay, so we'll write a function, and it is unsigned function f, and then int I, and we're going to return a value. Okay, we're going to return a natural number. So you can kind of look at unsigned as the set of all natural numbers in programming, and then you can look at int as the set of all integers. Now we know that is not true because there's a cap, there's a maximum of whatever number of bits you throw at an integer. It basically limits what is the largest value you can represent. But we'll just kind of borrow the notation from C and C++ to do this. Okay. Nope, not that. That is too simple. That's too easy. So the first thing we do is we want to see if I is less than 0. Okay. No, we are not done with the function yet. Okay, so this is not the function. This is just a part of the expression of the value that I'm returning, because this is going to be a ternary operator. So the question mark, is separating the condition that we're evaluating from the then value and then the else value. So the then value is going to say, let's multiply I by -2, and then we are gonna, let's see, I have to remember how this is supposed to work. And then we're gonna subtract 1 from it. There we go. Okay. So I use extra parentheses that are not needed. And then the other one is just I times 2. Okay. So this is the value that I'm returning, and close curly brace. All right. So now we want to know, so what does it actually do, right? Well, let's give it a try. So what do you think is f of -1? Okay, just kind of go through the algorithm yourself and follow along and see what value it is supposed to return. So because -1 is less than 0, so we go for the then value. The then value will then take -1, multiply -2 to it, so we have 2. 2 minus 1 is 1. Okay. What about f of -2? So -2 is less than 0. We go for the then value. So we have -2 times -2, which is 4. 4 minus 1 is 3. What about f of 0? 0 is not less than 0. We go for the else value. 0 times 2 is just 0. What about f of 1? 1 is not less than 0. We go for the else value. So we have 1 times 2, which is just 2. There we go. So in the end, what we are doing is we are mapping all the negative integers to odd numbers, and then we are mapping all the non-negative integers to even numbers. Is that okay? Does everybody see how we are actually doing the mapping? Imagine you're kind of folding the number line for integers, except after you fold, it becomes twice as long, because we are basically alternating between all the even numbers, which were non-negative integers, and then being interleaved are the odd numbers, which were negative integers before the mapping. So with this, okay, the question is, well, is this injective? Is this surjective? Is this bijective? So now we look at this f from a mathematical perspective. So we look at it and say the domain is the set of all integers, and then the codomain is the set of all the natural numbers. And now the question is, what do we know about this f in terms of injection, surjection, and bijection? So let's evaluate those. Okay. The first question is it an injection? In other words, do we guarantee to map 2 different integers to 2 different natural numbers? What do you guys think? Yeah, I would think so, right? Because positive and negative certainly would be different, because one would be an odd and the other one would be a even number. And then between 2 non-negative values, because we are multiplying each one by 2, so the result of the multiplication by 2 would also be different. And then a similar argument can be applied to the way we do the mapping from the negative integers to the natural number, because we have to multiply by 2, and that kind of guarantees that it is injection. Okay. So the next question is, what about surjection? Okay. In other words, do we use up all the natural numbers mapped to? If I just randomly pick a natural number, can I say that, yep, some integer is mapping to this natural number? Are we using all of the elements in the codomain? That is the question when we ask, is it a surjection? All right, I'm not seeing any answers from the text channel, but the answer is yes. Okay, if you just pick a natural number, we can go back and figure out, what integer maps to it. All right, so that means it is also a bijection because it is both an injection and a surjection. So I'm just going to pause a little bit here and see if you guys have any questions right at this point, just to absorb the fact that this particular function f is injective and it is surjective, and therefore it is a bijective function. Surjection means, if I just pick a particular natural number, I know which integer maps to it. In other words, I cannot find a natural number that is not mapped to. All right, cool. And then we got another question coming. All right, so looks like we don't have any questions. So now, do you remember, if we know a function is bijective, we know that there's an inverse. Okay, there's a way to go the other way around. So now the question is, what about this function f? What is the inverse of this function f? So let's figure out how that can be expressed. So this time we have int as the result because we're looking at f inversed, and then the parameter is going to be unsigned, and we'll call it I again, and see what we're going to return in this case. So the first thing we need to do the f inversed is to see if I as a natural number is odd or even. Because if it is odd, that means we have to map to an integer, negative integer. If it is even, then it maps to a non-negative integer. Okay, so that's relatively easy to check. So we say f mod 2 equals to 0 is the condition. If it is true, that means we have an even number. If it is false, that means we have a odd number. We're referring to I. Okay, if I mod 2 is a 0, then I is a even number. If I mod 2 is non-zero, then it is a odd number. Okay, so what we put here is going to be the case for the case when it is a natural number, when it is a even number. Okay, when I is an even number. So that's pretty easy. We just have to say, I divided by 2 is what we want to return. Because, 2 maps to 1, 0 maps to 0, 4 maps to 2, 6 maps to 3, and so on. Okay, so it's just a division by 2. Now we get to the case when it is an odd number. Okay, so when it's an odd number, what do? So we basically have to reverse this operation here, which means we have to reverse the operation from the outside in. So the first thing we do is we add 1 to it. So I plus 1, the whole thing, divided by negative 2 is what we're going to return. In other words, if we start with 3, then we add 1 to it, it becomes 4. 4 divided by negative 2 is negative 2. Okay, if we have 1, okay, if I is 1, then 1 plus 1 is 2. 2 divided by negative 2 is negative 1. So we have just mapped 1 to negative 1, which is exactly the opposite of what we have over here. So f is both. So f is injective surjective, and bijective, and as a result, it has an inverse function that is also bijective. Are we doing okay so far with this specific example? All right, cool. So what is the big deal, right? I mean, how does this have anything to do with the comparison of the cardinality? Well, this shows that they have the same cardinality. Okay, so let's go back to the notes, okay, because I want to use the notes for this. So if we go back to the notes, basically I use exactly kind of the same example. The equations can be different because I flipped the comparison. So instead of asking whether x is less than 0, I'm asking whether x is greater than or equal to 0. But the bottom line doesn't change. The bottom line is because f is a function, it is a bijective function that can map a particular set to the set of all natural numbers. So now the two sets are said to have the same cardinality. So switching back to the tablet, by definition, by DEFN, by definition, the cardinality of the set of natural number is aleph null. Okay, that is how aleph null is defined. And I have to remember how to write aleph null. Okay, it looks like a squiggly N. Okay. So getting back to the tablet. So by definition, the cardinality of the set of all natural number is aleph null. Okay, that is just the definition. But because f as a function, it can map the set of all integers to the set of all natural numbers, is bijective. And I have to say, because there exists at least one function. In other words, there may be a whole bunch of functions that can do the same thing. All I need is at least one function that can do this job. Okay. Therefore, oops. There we go. Therefore, the cardinality of the set of all integers is the same as the cardinality of all natural numbers, which is aleph null. Okay, am I doing the squiggly the right way? Yep, okay. There we go. Cool, isn't it? It is really odd, right? Because it's counterintuitive. It is counterintuitive that the set of all integers actually has the same number of quote-unquote the same number of elements as the set of all natural numbers. But the way we show they have the same cardinality is through the function f in this case, so that we can have a basically a bijective function to map between these two sets. And whenever we can establish a bijective function between a set and the set of all natural numbers, the other set will also have a cardinality of aleph null. So do we have any questions? Oh, we are running out of time, so I better stop at this point. All right, so what you need to do is we have a homework assignment that's due in a week, okay, a little less than a week because now we have used up 1 hour and a half or so. So that's one, but I also want you guys to finish reading this particular module. So even though we have just defined what is aleph null and one particular application of the concept of aleph null, I want you to go through Section 5, because Section 5 is a very interesting map. This function g is really kind of interesting. I want you to read through it. Okay, some of the math you may. Okay, if you have taken Math 372 or Math 370, the math used in the rest of this module, you should not have a problem with it, because the worst part of this is quadratic. Okay, and quadratic equations is not a big deal, if you have taken Math 370. So just read through all of this stuff here. Okay, I know at certain times, it's going to look a little bit complicated. It's more complicated than it really needs to be. But the bottom line is, if you have a two-dimensional space, and we are talking about a discrete two-dimensional space where x and y are have natural number as coordinates, which is kind of like a screen, right? That space has the same cardinality as the set of all natural numbers, which doesn't seem to make sense, right? Because you have a two-dimensional space, and I claim that it has the same cardinality as the set of all natural numbers, which is a single number line with only one end extending. So it doesn't seem to make sense, but it can be done, which is what the rest of this module is trying to do. So we are done here. Yes, so Aiden, it is correct. In fact, n, the Cartesian product of n with itself, as long as it is a fixed number of Cartesian products, it still has the same cardinality as n, which is weird. Okay, so I'll write it here. Okay. As long as this I is a specific number. Now that is not the case, because the natural number set has a doesn't have a fixed number. Okay, the cardinality of n is not a fixed particular value, so there's no such thing as n to the power of that n. You cannot take an infinite number of Cartesian products. But for any known I, and I is a number that is at least 1, then the cardinality is just that. That is not R. I don't know how R is expressed. I would probably guess that's aleph 1 or aleph something, but it's not aleph 0, because we are looking at different types of countability in this case. Alright, so lecture is done today. You have homework assignment due in a week, and I want you guys to finish reading this module before Wednesday so that we can start to talk about the function g, which is a kind of cool function mapping any dimension space to a natural number set.